Continuing the elevator lab, we're now going to look at some force diagram analyses and actually show how to calculate the net force and the resulting acceleration for each part of the man's trip in the elevator. Okay, so we'll start with when he was at rest at the bottom. And so we've already seen this force diagram, but let's just draw it again. So we said that the two important forces in this situation, there is the gravitational force that the Earth is exerting on the man, and there is the normal force that the scale is exerting on him. And in this situation where he is not moving, he's at rest at the bottom. By Newton's first law, we know that the net force equals zero, right? Even before we analyze these forces. So these two must be congruent. The normal force and the gravitational force are balancing each other. His velocity vector is just, he doesn't have a velocity vector because he doesn't have a velocity, right? So on a motion map, we would just put the position dot to show where he is. And similarly, there is no acceleration. There's no change in his velocity. It just continues to be zero while he's at rest. So there is no acceleration vector. And his acceleration, which equals the net force divided by his mass, equals zero. Okay, let's look at another situation where the elevator is starting to move upward. So it is speeding up, right? Because it was at rest and now it's starting to move. Let's look at the force diagram for this situation. So the gravitational force on the man that's being exerted by the Earth has not changed. I'll just go up and find that. That is 909 newtons, so we can fill that in. But the reading on the scale, which we now know is the normal force, is larger in this situation. So the normal force that's being exerted on the man by the scale equals 999 newtons in this situation. And I'll just remind you where I got that 999. I'm looking here at the reading of the scale, of course converted to newtons, but the reading of the scale as the man was moving up from the ground floor to higher floors. Okay, so the man's velocity vector would point upward because that's the direction that he's moving. He's speeding up, and so his velocity vector is in the same direction as the acceleration vector, also upward. The net force equals the normal force minus the force of gravity, and so that equals 999 minus 909, so that is 90 newtons. And the acceleration in this situation would be that net force divided by the man's mass, which is 90 newtons. It just occurred to me, I don't think we've calculated his mass. Let's go do that. So we were supposed to do that back here. So remember that force of gravity equals the mass times acceleration due to gravity at the location. So the mass is the force of gravity divided by g, so it would be 909 newtons divided by 9.8 newtons per kilogram. So the man's, 909 divided by 9.8, his mass is 92.76 kilograms. Okay, so now that we have that, we can use that to find the acceleration. 90 newtons divided by 92.76 kilograms. We get an acceleration of 0.970 meters per second squared. Okay, let's look at the other situation. If he's going up at a constant speed, his velocity vector is upward, his acceleration vector is 0. There is no acceleration vector because there's no acceleration. The net force is 0. Newton's second law tells us, first law tells us that, because he's moving at a constant velocity. And so the acceleration, which would be the net force divided by his mass, would also be 0. Okay, so I won't take the time to draw that force diagram. It would be the same as the one in part 1 up there. But let's look at this more interesting case where he slows down as he nears the top. Okay, so the force of gravity on this man still has not changed, right? The force of gravity that the Earth is exerting is still 909 newtons. But if I go up to the table and look at the reading for when he was slowing, the elevator was starting to slow down as it neared the top floor, the reading changed, and so in newtons it was only 837 newtons. So now the normal force is smaller than the force of gravity. The normal force on the man by the scale is only 837 newtons. Now he is still moving upward, so the velocity vector points up, but now he's slowing down, and so the acceleration vector goes in the opposite direction. The net force is the normal force minus the force of gravity, which is 837 minus 909. Look at this, it's going to be a negative value. And we get negative 72 newtons. And so the acceleration is that net force divided by his mass, which is negative 72 newtons, divided by 92.76 kilograms. Is negative, we've got a negative acceleration, 0.776 meters per second squared. So the reason that the weight or the reading on the scale changed is because the man's acceleration changed, and in order for the acceleration to change, there had to be a different net force.